All right, good evening. Welcome back to statistics, and we are going to be taking a look at test of hypothesis. This is section 9.2. All right, let's go ahead and share screen and get started. Okay, there we go. Get some paper out here. Let's see what we have. All right. So going back to chapter 8 here. So we have a 95% confidence interval for mu. And it's computed to be between 1.6 and 3.4. For the following hypotheses, state whether or not HO will be rejected. Okay, so it says HO, or no hypothesis, is going to be 2 versus the alternative, H1, that mu is not equal to 2. Well, look at my confidence interval here. It is clearly, like 2 is clearly in this interval. Okay, so we are going to be able to say that, we're not going to reject that hypothesis. Okay, so HO we will not be rejecting HO. So if this contains HO will not be rejected. All right, be able to say that. Okay, we're going to do several parts. Very good. Part 2, we're going to say mu is equal to 1 versus mu is not equal to 1. Okay, so if this was hypothesis, mu is equal to 1, mu is not equal to 1, our confidence interval does not include 1. So there's no way I would say that this is not going to be containing HL. So it does not contain H1 will be rejected at the 0.05 level. Okay. Notice that these are all lining up. Okay. So it'd be a lot harder to say if we had a 90% confidence interval versus a 95%. Okay, I don't want to put anybody in that position without more numbers to calculate these things. But in this case, we are clearly far enough away from 1, if this is my confidence interval, to say that 1 is not in that. Okay. 2.2 versus not 2.2. Okay, well, let me take a look. 2.2 is in here, so I don't have anything to say about that, right? I can only say that it contains it. Okay, so HO would not be rejected. Okay, so that's the kind of thing you're looking for. Oops, will not be rejected. Okay, and the last one is a 4.3 or not 4.3, and again, this is much higher. 4 is way higher than this confidence interval, so. Since the confidence interval does not contain HO or mu0, HO will be rejected at 0.05 level. Okay, that's exactly what they're looking for. So confidence intervals and test hypothesis tell you very much the same information. It's just that with a confidence interval, you may not know the percent confidence interval. Okay, whereas the hypothesis, you will know the percent. Okay, but they're very much tell you the same information, just in a slightly different way. Okay, let's see. Charlie will form the hypothesis. This is why I tell you that you should definitely pick your level first, your alpha level first, because that's going to change what's going on here. Okay, so Charlie will perform the hypothesis test at alpha equals 0.1. Felice will perform the same test at alpha equals 0.05. So they have a 0.1% chance of making a type 1 error and a 0.05% chance of making a type 1 error for Felice here. Okay, so Charlie will have a higher percent chance. Okay, Charlie will have a higher percent chance of making a type 1 error. Okay, if HO is false, who has a higher probability of making a type 2 error? So again, remember that if you clamp really down on one of them, the other one tends to go up. Okay, so we're looking at who's making, this is 0.05, so Felice is actually getting a higher chance of making that type 2 error here. And that was it. Okay, very well. I promise it'll. Okay, there we go. So in this case, right, we are knowing that sigma is known. Okay, so we say a test, we have HO mu is equal to 20 versus H1 mu is not equal to 20. We have a sample size n is bigger than 58, and x bar equals 50 is equal to 18. Okay, standard deviation, population standard deviation is 8. We're going to go ahead and compute the test statistic. Okay, and then we'll see what happens. Okay. So in order to do this, okay, what we're going to do is we're going to go to stat. Okay, we're going to go to tests. Okay, and we're going to hit z-test. Okay, just like a z interval was a interval with a known sigma, we're going to go to z interval. Okay, so first thing we're going to do. Okay, so we're going to, let me just show you the whole thing to set it up. Okay, so part one, step one here, they did this for us, and most of the time they will do this for you. Okay, say HO mu is equal to 20. H1 alternative hypothesis mu is not equal to 20. Okay, so remember that the null hypothesis always gets the equality, the alternative gets the inequality, whether that be greater than, less than, or whatever. This would be a two-sided test. Okay, and what other pertinent information we need in here is we need mu, or x bar rather, is equal to 18. So we're going to say x bar is equal to 18. We have a sample standard deviation, or a population standard deviation of 8. Okay, that's how we can use z. So because we have this, we're going to say use z test. There's a t-test too. Okay, that's the next section. And we're going to compute some values here. Okay, so they want to know what's going on at different levels. Okay, so we're going to actually have a part B and a part C where alpha equals 0.0 or what is it, 0.1, 0.01? What do they say? 0.05. Alpha equals 0.01. Okay, so we're going to make sure we've written that in. All right. So our step one, okay, is to write down our hypothesis. This is technically step two, where we're going to go ahead and specify our level of significance. Okay. Part three here is we're going to calculate our test statistic. Okay, and there's different books that, I mean, there's other books, other test of hypotheses where you can test other things. In this case, it's going to be the z statistic because sigma is known. Okay, so here we go. Okay. We're going to hit z-tests. Okay, yours is going to be a little bit different than mine. We're not going to be inputting data. We're just going to be inputting some stats. They can give us a list of numbers, and we would have to put in that value, put in those values. But our mu is equal to 20. Okay. Our standard deviation is not 0. Our standard deviation was 8, I believe. There it is. Okay. No, I didn't want data. I wanted stats. How do I change this? Enter. Okay, there we go. So mu is equal to 20. Standard deviation is equal to 8. X bar, that was what we found. Okay, so we found that X bar is equal to 18. Did they give us an n? It had to, n is equal to 58. So we're going to go ahead and put this in here as well. N is equal to 58. Technically, I guess we could list all of these values right here. We could say X bar is equal to 18, standard deviation is equal to 8, n is equal to 58. Okay, so we would group all the information in a place where that would be nice to have it. 58. Okay, we're going to hit mu is not equal to. Okay, so this is what we want, is not equal to a value, and then we're just going to hit calculate. Okay, so our test statistic z, this is negative 1.90. Okay, so let's go back over here. We're going to hit, so our test statistic equals negative 1.90. Again, the computer does all the heavy lifting on this thing. Okay, we're going to be using something called the p-value. That's this guy right here. Okay, right here it says p. This is 0.056. Okay, 0.056, we'll say 9. Okay, again, it's a probability, so 4 decimals is probably the proper thing to do. Okay, now the fourth step, okay, this is where you actually have to think about things. So it's going to say if your p-value is less than your alpha value, then reject the null hypothesis. Okay, pretty much, and if it's greater than, okay, otherwise, p-value is greater than alpha. Okay, do not reject. So I'm going to tell you rather a sad and a little bit morbid story about this. This is just how I remember it. So you're going to need something from your own experience or your own history to kind of get the idea here. But you're setting a level of probability. Okay, so there's lots and lots of horrible things that that different companies, different entities will do to its people. Okay, so it's well known that populations that live near an oil refinery, well, those kids have lots and lots and lots of respiratory issues. Okay, and if you go up to the oil refinery people and they say, "Hey, look, all these kids have respiratory issues. You think you could like maybe pollute a little less for us because we don't want to die living downwind from you?" And the oil refinery will say, "Well, look, that's just random chance. It's not our problem. Those kids could have gotten respiratory issues without us being here." Like that's entirely true. However, what this p-value, what this alpha is doing, you're going to say, well, look, if it's less than a 5% chance that these kids could have gotten the respiratory issues without the plant, then we're going to say, you've got a point. It's unlikely that these kids would have respiratory issues with or without you being here. Okay. However, if we have, if we find that it's less than a 5% chance that all these kids would have respiratory issues, we're coming back for you. Okay. So when I was growing up, I grew up in Pennsylvania, which is near New York. There was a development called Love Canal. Okay, I'm not kidding. It really was that. Okay, stop thinking anything like that. And what they did, what the property developers did, they bought a whole bunch of property that all these power plants, they eventually went out of. It was downstream from like Niagara Falls. So there's lots of hydrochemical plants up there, and these plants didn't really have much care for the environment. They just that's that's a toxic chemical. We're just going to dump it in the ground because nobody will ever live here. And later, these property developers came and they said, "We would like to buy that property and build houses on it." And people said, "Well, we don't really care about the property, so here you go. We'll sell it cheap. Take it." And the developers said, "Great, we're going to build houses on it," and they did, and people moved in. And it came about that kids that were born in those developments, they had a lot of weird cancers, a lot of weird diseases coming from the fact that people were dumping all this toxic, all this industrial waste on that land from before. And they went to the people that living in the houses, they rightly got together and they said, "Hey, you got to clean this up." And those power companies said, "This is not our problem. These kids could have gotten these cancers and all these diseases with or without us there. You can't prove that." So what they did is they got together and they said, "We think it's unlikely because these were all a bunch of really rare cancers. Like it's less than 5% likely. It's less than 1% likely that these kids would have gotten these diseases if we didn't happen to have built a bunch of toxic waste dumps." And eventually they won their case. But the picture I always have in my head for doing this, okay? So you're looking at your p-value. It's like you're setting up. Here's my standard. Okay, here's the standard. Now, if it's not less than 5%, then it's like, well, it's by random chance. That's unfortunate, but you can't really assign blame to anybody. But if we get this p-value that's really small, the probability falls way under the standard, and say, it is extraordinarily unlikely that all these people, all these kids got these horrible diseases just by random chance, right? So we're going to go off and we're going to be looking for something else to say that thing is to blame. Okay. So what you're looking for is saying, okay, here's a standard. And then here, reasonable standard, 5% is usually considered reasonable. Because again, you're going to clamp down on other problems if you clamp down too much on this. Okay. But if our probability is so under, like this is a random chance sort of event, we're looking for an alternative cause. Okay. So HO is, well, I don't have enough proof to say the company or whatever caused this issue is a problem. But if this probability is so low, there must be an alternative explanation. Okay. So p-value is less than alpha. We're rejecting the null hypothesis. Like, no, I don't think it's by random chance. We're looking for an alternative. Okay. Otherwise, we're going to say, yeah, we can't prove it. It's just bad luck. I guess we don't have enough evidence. And it could have been by random chance. And what are you going to do? So since my p-value, right? So you have to look. Okay, since my p-value is greater than alpha, it's not less than alpha. Okay, we could say it this way. P-value is not less than alpha. Okay, we say, well, do not reject. And all you're doing is you're saying something like, look, you're not off the hook. Okay, but I don't have enough evidence to actually say that you did it. Someday I might, but it's possible you still did it, but I can't do anything about that. So we do not reject the null hypothesis, and you say, well, I guess it was by random chance until we get some new evidence or something else comes to light. Okay. So in this case, the test statistic, this was 2 decimal places. So this was negative 1.90. Okay, negative 1.90. Okay, check. All right. This is a two-tailed test. Why are they doing critical values? All right. So they want, it's going to be negative 1.90 and positive. Okay, no, I'm wrong. Hold this thought. Okay. I gotta learn how to do it on a calculator so I can show you. So give me a moment. I gotta just run through it on a calculator. I'll be right back. All right. So what we have to do for critical values, which is a little odd because we don't teach critical values anymore, but it is an easier way to do this. Okay. So the idea here is for critical values, okay, what we're going to do is we're going to do inverse norm or inverse, I'm not sure which one it is. And then for 0.05, okay, so what happens with a 0.05? We're going to look at our normal curve. And we're going to say the middle part here, this is all 95%. This is 0.0, this is 0.95. How much we got left? 0.05. So I've got a nickel left, and I have to split that nickel and put it into each of these pockets. So this is 0.025, okay? And for 99%, right, again, we have, here's our 99%. How much you got left? You got 1% left. Okay, so these pieces here, this has to add up to 1%. So if we're going to break these things into two pieces, I've got to put half a cent in one pocket and half a cent in the other pocket. So I've got 1 penny left over. Okay. So to get our critical values, what they're looking for is like, what's the probability that it's going to be up to here? Okay. Or given that the probability is 0.025, what Z value, what is our cutoff? Critical values are cutoff values. So we're going to do second function distribution back to our friend inverse norm. Okay, we're going to put in the 0.025, that's our probability, the 0 and 1, because we're talking about a standard normal here. Okay, and we're going to get to two decimal places, we're going to get to 1.96. Okay, so this value here, this is 1.96. Okay, now we get to fold over this thing because the normal distribution is symmetric. So the positive side of this is 1.96. Okay, and the reason we use standard normal is so it's easy to figure out what these two values are going to be. You could do them with anything you want, but it has to be symmetric about the mean, okay, with the standard deviation as a step. Since normal distribution, the mean is 0, the step is 1, it's real easy to figure that out, okay? So here we're going to do inverse norm, okay, 0.00501. Okay, so look at that. We're going to say second function distribution norm inverse, okay, 0.005, 0, 1, enter, boom, -2 or 2.576 is usually how this is written, okay, or 2.58. Okay, so this value here, this Z value here is -2.58. This one up here is +2.58, and that's how we're going to figure that out. Okay, so you can get critical values for lots of things. 1.96, +1.96, and then for the next one is 2.58, 2.58. Okay. Let's see, how many decimal places? 3 decimal places. Oh, this is 2.576, 2.576. Okay, if I look back at my calculator, to 3 decimal places, 2.57. The 8 comes up and rounds us to a 9, or to a 6 rather. All right, so it's a two-tailed test. That's what our values are going to be, and we'll be okay with that. Fingers crossed. Oh, I forgot the negative. Okay, glad that flagged that for only that little bit there. Okay, since our test statistic, okay, is in the critical region, okay, so we're going to say our p-value rate is less than that. Our test statistics could be not as small as what it needed to be, because in order to reject, it's got to fall into the rejection region, which is smaller than -1.96. We're a little above it. Okay, so this test statistic is not in the critical region. We do not reject the null hypothesis at this level. And the same thing is going on here. Okay, so the test statistic is not in the critical region. We do not reject the null hypothesis at the 0.01. Because 0.01, you got to be, more than -2.576. And our critical value, right, that's 1 point, our test statistic rather, -1.9. It's not smaller than. I know this is a little bit on the confusing side, and we're going to confuse you even more because we're going to switch to a different method in a moment. Okay, and I apologize for that. I'm sorry. But here, let me draw you a little picture. All right. So say we're alpha equal 0.5. So if our p-value is smaller than 0.05, that's going to be in here. Like it's going to be somewhere in this probability. What's the cutoff region to get me my 0.05? This was 1.96. So if we are going, this is called the rejection region. Okay, I don't think that the rest of the book really does anything with this for us, so we're not going to worry about it too much, but that's what that vocabulary means. We ended up with -1.90, not in the rejection region, so we do not reject the null hypothesis. Okay, it could also be greater than 1.96, and if we ended up with a probability up here, right, or a rejection, a z-value that's somewhere in here, test statistic that's somewhere up here, we would also not reject. Because two-sided tests, could either be here or it could be there. All right. So that's what we're doing with that. So that's what they mean by this. In times before, we didn't go through and calculate p-values because it was an extra step that you didn't need. If you just calculated these, it was one less chart you had to consult. Okay. But culturally, scientific literature, culturally, people wanted to go more toward a p-value than the critical value because the p-value gave the reader a little bit easier time. That's where we migrated to. So back when I took this class, we used this because, again, it was one less chart you had to consult. We didn't have these calculators. Now we have the calculators. They usually do the p-values instead. Okay. There was a brief resurgence of using confidence intervals rather than test of hypothesis. I wish that was stronger, but I don't think it was. So here we are doing it this way. All right. So I want to try another. I want to go on. Okay, Facebook study. Good Lord. Study showed that 2 years ago, the mean time spent per visit to Facebook was 20 minutes. If only it was that easy. Assume that the standard deviation sigma equals 8 minutes. Suppose that the simple random sample of 104 visits was selected this year, and we had a sample mean of 19 minutes. Social scientist is interested to know whether the mean time on Facebook visits has decreased. Use our alpha equals and get our p-value from the p-value rather than critical value on the calculator. So what does the scientist want to know? He's saying, I think people are going to Facebook less. If only that were true. And spending less time on it. Again, if only that were true. But we're going to test that. Okay, so here we go. We're going to say HO, H1. Okay, we were given that 2 years ago, the average time spent was 20. This social scientist wants to know if that mean time is less than 20. Right? The time is decreased. So we're going to say mu is less than 20. So this is now a one-sided test. All right. They tell us we want to test this at alpha equals 0.01. Like, okay, that's fair. Right? And here's why. They did a terrible job demonstrating this in the last problem, but since there was so much going on there, I don't fault them too much for that. Okay. The reason you want to declare your alpha, your standard up front. What if you have a social scientist trying to study this? I think it's less. What if they don't find it's like to this level? What if they find the p-value is like, you know, what if your p-value is 0.03 and you're writing a story for a paper or something, and your boss comes to you and they say, you know, it would actually be good for us to make the news that people are spending less time on Facebook. Are you sure your p-value needs to be, are you sure your alpha needs to be 0.01? Couldn't you say it was alpha equals 0.05? And then all of a sudden you pass the test, your experiment was a success. Okay, you get to keep your job. Yay. I've never been put into a position where they have said, you want to change are you sure you want to change your standard? You know, it'd be really nice for the company, it would be really nice for our profit region. It'd be really nice for your job if you had some flexibility on this alpha. So I've never been put in that position to do that. I've never been put in that position where I've like bought a new house and I have kids and things happen. But you can see where your ethics may be called into question for doing this. Okay, this is not what you're supposed to do. Okay, you're supposed to do the experiment. You're supposed to set your alpha up, do the experiment, and then make the decision. You don't get to see what the alpha or what the p-value is going to be, then set your standard so you can make the decision that somebody else wants. Which is why I tell you, like, some books will say, let the reader pick an alpha, pick a level of significance. Like, well, then everybody gets to pick their own answer. That's not good. So you pick a standard, do the experiment, and then make the decision based off of that standard that you set up before you knew the answer. Okay. Otherwise, you get pandemonium here. Okay. So here is our pieces. Step 1, set up the hypothesis. Step 2, set your level. Okay. Step 3, we're going to calculate our test statistic. Okay. And then here we go. We have, right? We don't need mu. We need X bar, right? What was our X bar? All right. Our X bar said it was 19 minutes. Okay. Our N was equal to 104. And we're going to go ahead and use our sample standard deviation. Okay. Of 8. Okay. So here we go. So we're going to go to stat, tests, the z-test. No, this is the first one. Okay. We're going to stay with stats. We're going to go to mu is equal to 20 still. Okay. Sigma is still 8. That's kind of convenient. Sigma X bar is equal to 19. This guy here is 104. We visited 104. We analyzed or looked at 104 visits. Okay. And they want to say less than. Okay. Yep. Less than. Calculate. We don't need the draw. Draw is going to be nice, but we don't need to do that. Okay, so p-value 0.1012. Okay, our p-value. I'll say the p-value is 0.1012. Okay, just double check in here. Yeah. All right, so our standard is the 0.05. That's what we set out at the beginning, right? So that's what we have to compare. Oh, 0.01, sorry. We want a 0.01. Okay. So our standard is comparing it against that. Okay. You've got to bet a dime here, right? P-value equals 0.1012, and our alpha is equal to 0.01. Is p-value bigger or smaller than alpha? Right? You have a dime versus a penny, dime versus a penny. I'd rather have the dime, so this is a bigger number. Okay, so p-value is not smaller than alpha. Okay, so we're going to say, well, look, we set a standard of 0.01 if we found that the probability that it happened by random chance is 0.01. Our random chance was 10% rather than 1%. So we say, well, it's random chance. We're not gonna make a conclusion. We're not gonna make the alternative conclusion here. So we say, do not reject the null hypothesis. Well, 10% was kind of a small percentage. It didn't make it to the small percentage that we had set as what we're going to take for our answer. Okay. So do not reject the null hypothesis. No evidence to suggest Facebook visits are getting shorter. Okay, so here we go. Null hypothesis. Okay, mu equals 20. Okay, again, some books will do a greater than or equal to here, and alternative is mu is less than 20. Right? Alternative hypothesis always gets the inequality sign. Okay, this is a one-sided test. It's a, what side do we care about? Okay, we're caring about less than, so we're saying, right, here's 20, we want to know what's going on over here. So this is a left side test. Okay. No, really, check. All right. Okay, calculate the p-value. That's our second level here. Okay, we're actually at step 3. Our p-value was 0.1012. Okay, so this was 1012, a little bit more than a dime. Okay. All right. Determine whether to reject HO at the 1% level of significance. Okay, we said that that p-value is pretty high, so we're not going to reject the null hypothesis. Okay, and then on your quizzes, you have to write something like this. Okay, the book will kind of like drag you through it, and it doesn't have to be this formal. You could just tell me like Facebook visits are not decreasing in duration. The time people spend on Facebook is not decreasing. Okay, you don't have to go through all of this. It's great that you can, or it's great that you would, but if you at least write a sentence, like you're going to write something to somebody who's going to say, oh, you did this research. What was your conclusion? Facebook visits are not getting shorter. Okay, there is not enough evidence to conclude that the mean time for Facebook evidence has decreased. Okay, that sounds good. Okay, but you are not on the hook to write this. I just want to make that really clear. Write it in English. Okay, so I'm going to stop here so we can do some more later, and this won't turn into a video that's forever long. Okay, so thank you very much for coming in. I'll finish this off in the next video.